So our next speaker is Professor Dina Katabi. She is she is Angel and Erna Viterbi professor, and also MacArthur Fellow. She's also one of the youngest members of American Academy of Engineering. She's going to introduce her wonderful research, innovative research at the home touchless monitoring of sleep and vitals using AI and radio signals. Let's welcome Dina.
Hello, everyone. My name is Dina Katabi. I'm a professor at MIT. And I work in the area of machine learning that analyze radio signals. And analyze them particularly in the context of two types of applications. One of them is healthcare, and the other one is IoT-related applications. So I'm really happy to be today with you. It has been a long time since we got to present in person, so it's great to see all of you guys here. So when I tell people that I work on applications that can sense your sleep, your vital signs, and all of these kind of like physiological signals, people think about wearables. So they think, oh, computer scientists, this is like a new wearable technology. And I tell them, no, actually, it's like a new concept that we think about in my group at MIT, which we refer to as the invisibles. So if you think about the last 2 decades, like basically we saw the rise of the wearables, we think that the next 2 decades, probably we are going to see novel technologies that we refer to them as invisibles. Basically, can we monitor things that are related to our activities, behavior, motion, vital signs, sleep, all of that stuff without asking people to wear sensors or to do anything. Just let people live their lives and let the environment be smart and be able to analyze all these physiological signals in a touchless manner. So how do we do this? So all of you guys have a Wi-Fi box at home. In fact, now you are sitting here, you are immersed in radio signals, all types of these radio signals, whether Wi-Fi, cellular, etc. So what we do in my research group is we design new machine learning algorithms that analyze radio signals that bounce off people's bodies. And from that, you can get breathing, heartbeats, sleep stages, movements, activities, and many other things in a touchless manner. We call these new boxes. They are very much similar to your Wi-Fi box. It sits in the environment, and we call them an Emerald wireless box. So I'm going to start by showing you an illustrative example. So in this video, what you see is a home. The wireless signal, of course, spread inside the home, traverse walls and occlusion. It reflects off our human body because the body is full of water. And some of these signals come back to our device. We analyze them using machine learning. In this case, we detect a fall. We can alert the caregiver via text, email, or a phone call. Let me show you some of the experiments from our lab. This is actually one of the early experiments that we did on tracking people completely contactless through walls and be able to see how they are moving. So you see one of my students standing in one of the offices that we have in CSAIL. And what you see on the side, you see this red dot here is where the device thinks that he's standing. You see also an arrow that is pointing at the wall. This is where the device is in the adjacent office. As he moves, look at the red dot, and how the device from the other office through the wall is discovering his motion. Completely touchless. There are no wearables. There is nothing. So we can track his motion in a completely passive way. He doesn't have accelerometers, cell phones, anything like that on his body. And we can do it just because his body changes the electromagnetic waves around him, and we can analyze those changes. So let's see it again. And we are able to localize and position this person as he moves in a completely contactless way through a wall. And the accuracy of this is we compare it with the Viking motion capture, which is like a whole room full of infrared cameras with a marker on the person. And the accuracy of positioning this person is 98%. So it's pretty high. Now, if you have such a device in someone's home, you can know how their motion. You can know, for example, when they sit on the TV couch, and so that you can use it for a smart home environment to tune the TV to their favorite channel. But you can use this also for a variety of health-related applications. Because take COVID, for example, fatigue, and it's very, very important and shows up as limited motion, staying in the same place for a long time. But not only motion. We can actually measure other things that you might not imagine that a wireless signal in the environment is a way to measure someone's sleep. Okay? So I can analyze the wireless signal in your home, and from that, not only I can tell whether you are asleep or awake, I can tell actually when you enter the stage of dreaming, the REM stage, without touching you, just by analyzing the signal that bounces off your body. So today, if you want to understand the sleep stages, so sleep stages are the result of changes in our EEG signal. And when we go to sleep, our brain waves change, and we enter different stages: awake, light sleep, deep sleep, and rapid eye movements. Rapid eye movements is the stage in which we dream. So of course, understanding sleep stages is important to understand sleep and sleep disorders, but also very important for a variety of diseases. Just to give you an example, depression, for example, is associated with REM starting too early in sleep. Alzheimer's, there is medical research that associate Alzheimer's with the slow waves in the brain during deep sleep. So if we can understand sleep stages, not only we can understand whether people are having sleep problems or insomnia, but we can get much deeper information about a variety of diseases. Today, if you want to understand someone's sleep stages, what you have to do is to send them to a sleep lab. They put these electrodes on his head and body, and they ask them to sleep like this. So you can tell he's not happy. And in fact, when I first started working with medical doctors and they told me this is how they evaluate sleep, I was really shocked because, I mean, you can imagine that for many people, this might not be representative of their sleep because they are sleeping with all of these electrodes in a new bed, in a new environment with all the sensors on their body. So it's not very representative. But it's not just that. Also, you cannot measure it repeatedly. You cannot send someone to have all of this on them and sleep in a sleep lab for a long period. For example, if you want to detect how a drug is affecting their sleep and sleep behavior. So here's what we do. This is our device. It transmits very low power wireless signal, 1,000 times lower power than Wi-Fi, analyzes the reflection using machine learning and neural networks, and spit out the sleep stages throughout the night. So you can see he's sleeping in his own bed, in his own bedroom, very non-obtrusive, and we can do this every night. And not only this, we can do it accurately. We did a study with Mass General Hospital in which we analyzed our system in comparison to the gold standard, which is called PSU. And we also looked at comparison with FDA-approved devices for measuring sleep based on EEG, as we mentioned. And actually, it's pretty accurate. The accuracy on characterizing every 30-second epoch is 80%, which is pretty high because at the end of the day, sleep characterization, sleep staging, is based on a technician looking at every 30 seconds and saying light sleep, deep sleep. And if you take the same signal from the same person on the same night and give it to two different sleep technicians, the inconsistency between them is about 83%. So 80% is actually comparable to what you get with FDA-approved mechanism. So OK, so we can measure sleep without touching your body, and we can also know your sleep stages. What else can we measure using these radio signals? So this person is sitting like you guys here, and he's reading. What you see on the screen is nothing but his inhales, exhales. We asked him to hold his breath, and you see the signal stays at a steady level because he exhaled, he did not inhale. And of course, it's not just visual. We compare this to FDA-approved devices for measuring respiration. In this case, is a chest belt, and the accuracy is 97%. And we can zoom in on the signal. So this is the same breathing signal that I showed you before. You see the inhales, you see the exhale. You see the blips on that signal. Those blips are his heartbeats. So these electromagnetic waves that are around us, they are actually very sensitive. Even the pulsing of our blood leaves a signature on those electromagnetic waves. And what you need to do is to reverse engineer that to understand the breathing of someone, their pulsing, their sleep, their movement, all of that stuff. Now, at some point, I was talking about this new technology. And I was in the audience. It happened to be somebody from one of the pharmaceutical companies called Leo Pharma. And they were particularly very interested in itching and scratching. He came to me after my talk like this, and he said, oh, this is great, but can you measure scratching using wireless signal? Today, the only way we can evaluate how bad someone's itch and atopic dermatitis is by asking them to rate it, to score it on a level from 0 to 10. And you just ask people, and you get something that is very subjective, because like me saying that my scratching is 6 may be very different from your sex, may be very different from some other person. So if they can measure scratching, they can actually objectively measure that and characterize itch level. And at the time, I said, I don't know, but if we can get pulsing, maybe we can get scratching. So let us try. And in fact, we worked with them. And we were able, from the bouncing of the radio signal in people's own bedrooms, and of course, we don't lead light or anything like, so we look at their nocturnal scratching, and we can actually evaluate it as accurately as if you had a camera there. But of course, you don't want to put a camera in someone's bedroom in reality, so we did it for the experiments. And let me show you this video. So this is from the labs. This is one of my students. And we did very similar experiments. So here, the classifier says no scratching. But as he scratches, you see that he says it's a classifier says scratching. But if the movement is not scratching, like when he puts back his hand, it knows that this is a movement, but is not scratching movement. And in fact, we can look at the false positives, the false negatives, and as you can see, the precision and the recall both are very high, around 90%. So I want to say a bit about how it works. Like, what is the underlying technology here? Now, of course, I don't have time here in this short meeting to tell you exactly the details of the technology, but just at a very, very high level. So basically, we transmit, as I said, very low power wireless signal. Now, you know that wireless signal traverse walls, and actually they reflect off our bodies, because as I said, the body has water, and as a result, these signals reflect off the body. But this minute reflection, imagine this is reflected off the body traversing walls and occlusions, and it's very minute reflections, and now it comes back to us, and we need to analyze them. Now, at a high level, one thing that we all know, and even like people who are not in like wireless expert, we all know that distance is equal to time multiplied by the speed of light. Okay? That's a very simple equation. So remember that dot that was moving, like positioning someone in space? So if we can analyze these minute signal, and from that understand the time it took the signal to go and come back, then I can multiply that time of light with the speed of light, and I can get the distance of a person. And then I can localize a person. That seems to be very simple. And in fact, this is actually underlying something like radar. For example, we all know about radar and like you track aircraft in the sky. The principles like that are used in radar. Now, unfortunately, it's not that simple. If it were that simple, people would have done this long, long time ago. So apart from the fact that we cannot really blast power like radar, like it has to be very low power so that it is safe for all people. The other thing that is very important is that actually the sky is empty. Okay? So you have like few aircraft there, but it's mostly empty. Like when you are talking about an indoor environment, there are so many things that reflect these wireless signals, not just our bodies. And that creates a huge challenge. So this is what we call, like if you come like me from a background in communications, this is called the multipass effect. So I come from communication from wireless cellular networks and communication system, and in that case, we tell you that the signal bounces off everything, and that creates a multipass effect. So as I said, the signal not only bounces off the person, but it bounces off many things in the environment, and also could bounce first off an object, and then off my body, then off another object, and start getting all of these fictitious targets. So you don't get just one reflection, you get so many reflections and fictitious targets. So these are the multipass effects. And then you have to ask yourself, now, how do I just take that signal and from that extract the human body? And not just I want to extract the human body. Again, the dot is good. I want to position someone, but that's not the only thing I want to do. I want to know also whether they are asleep or awake, and I want to know whether they are in REM, in the dreaming stage versus other stages. So I want to ask many other more complex questions than just position. How do I do this? Any guess? OK, I'm sure all of you guys have heard about advancement in machine learning and neural networks. And we have shown over the last decade that neural networks have completely revolutionized areas such as computer vision and natural language processing. Can neural network also revolutionize the way we think about electromagnetic waves? So this is what we do. We take these radio signals, we analyze them through a neural network that is particular custom neural network, and then we ask questions to these neural networks. We train them to answer those questions, such as, like, is this person asleep or awake? And if he's asleep, is he in deep sleep, light sleep, or REM? And what is their pulsing? All of those questions. Now, of course, this is not very simple. This is not just you're taking your neural network that you would use for analyzing images of cats and dogs and applying it here. There are many differences between the two types of signal, between electromagnetic waves and images. There are many similarities, but there are also differences. So I don't have time to get into the details. I just want to show you one thing that is really important. If you really want to take a neural network and to ask like question, make that neural network, take it to a new environment and be able to use it in my home to analyze my sleep, in your home to analyze your sleep, in Chris's home to analyze his sleep, then it has to generalize across people and across homes, correct? How do we do that? So say that you trained your neural network with some set of people, like say Bob and Alice and many other people. So those are the training people. And then you took your neural network to a new person, Chris, and this is person in new home, in new environment. So we call these like the training examples, the source environments, and Chris is the target environment. And now you want this neural network to generalize. And one of the problems, of course, I told you, radio signal reflects off everything in the environment. So they don't generalize well to new environments. So you have to design your neural network such that they can remove extraneous information irrelevant to the task. Let's say the task was like to monitor someone breathing or sleep. This is the relevant information. And irrelevant information are the information that are related to the environment. So Of course, how you do that is quite complex, but I'm just going to give you the first initial idea. What we do actually is more complex than that. This is the only slide that I'm going to show some technical information. So basically, if you are doing machine learning, then you are taking some input, whatever that input in our case is radio signal. You have some neural network. Typically, you have an encoder. You are trying to change your input to some representation that is easy to work with. So let's call this the representation E of X. And then you apply a predictor. In our case, let's say that you want to predict whether someone is asleep or awake or whatever you want to predict. Now what we want this representation, this intermediate representation, to have the relevant information, but to be free of extraneous information. So here's what we're going to do. We're going to make this work like a game. So we're going to add another neural network, which we call the discriminator. The job of this neural network is to look at this representation and try to predict whose home that was. Okay? So the discriminator is going to look at this and going to say, this is Alice's home, this is Bob's home, this is Chris's home. So he's going to look at all the things that are irrelevant to the task that come from the environment. And what we're going to do, we're going to train this combination of multiple neural network in a style that is what we call an adversarial game. So the objective of that game is to make the discriminator lose at the end and make the predictor win. So eventually, the predictor will be able to predict, while the discriminator, the neural network that's trying to extract all this irrelevant information, is just going to lose, will not be able to extract that irrelevant information. And we can do that through a training function that is a combination of of the predictor loss and the negative of the discriminator loss. OK, so that's what I'm going to say about how it works. Now let's see what we can do with it. So I showed you that we can track someone's location. And you saw this video, but when he was moving, you saw the dot, you know where he is. But you can't tell whether he's standing or sitting. Like you look at this dot, you know where he is, but you don't know, is he standing or not? Also, when he was moving, he was sliding. You didn't see whether he was stepping with his right foot or left foot. So what we can do, this is our older version. Now, here's our new system. Our new system can get the full skeleton of the person. And this is through wall. And I'm going to play this video. This image up there is just inside the room, just for you so you can visualize. And the big frame is what the wireless device gets. OK, so let's play this video. So you see when he sits, the device now sees that he's sitting. And you can see when he stands, actually it knows that he's standing. When he's moving, it knows when he advances the right foot, when he advances the left foot. So not only we are getting a dot through a wall, now we are getting a full representation of the human body through a wall. Effectively, we are getting a form of X-ray vision. Like if you read about Superman when you were a kid, and we are moving, taking one step closer to that Superman, seeing the full skeleton of a person and their movement through a wall. So we also looked at whether we can predict their actions. So let me play this video here. So you see when the person, for example, tries to emulate combing his hair, the skeleton is combing his hair. And the machine learning model says combing the hair. When he tries to emulate drinking water, you can see the skeleton looks like he's drinking water. And then he tries to pick up something and put it in his pocket. You see that in the skeleton. So we are getting very much information that is related to behavior and action. Now, there are many applications of this kind of technology. And in fact, the way to think about this technology is really it's a novel, invisible IoT technology. Is these IoT devices now, we have them deployed in people's homes, and they extract information about health and behavior. And one of the biggest applications that we have partnered with many institutions, and both in pharma and in hospitals, as well as other institutions in the healthcare. And They have been using these devices to analyze diseases and analyze how people behave and different biomarkers for different diseases. I'm going to talk about some of these experiments actually with in people's own homes within certain diseases. And let's look at how effective that is. So this is our device. And as you can see, I mean, it's just like a very non-obtrusive device. It's on the wall, and just the person can forget about them. And of course, as I said, it's an IoT network. This is a device in the home, but it's connected to an IoT network. I want to show you first some of the results from our Parkinson study, because this was one of the earlier studies that we started with. So let me first show you this example. So this patient, you can see the green rectangle at the top. This is our device. We call it the emerald device. And you see blue line. This line is the trajectory of movements of this person for about 2 hours. And you can see it goes between the bed, the chair, and the bathroom, etc. Now, this is just a dot. Even that dot, and we are beyond that dot, but that dot on its own is very useful. So let me show you what we can do with this. So we put this device with patients who have Parkinson's for a long period of time, and the doctor was interested in understanding their behavior and how the disease impacts the behavior. So let me explain this graph. So this graph is for the same patient on this slide. All right? So every circle in this graph is 1 day. The top number, you see 0 at the top. This is midnight. And at the bottom, you see 12, which is noontime. So every circle is 1 day. The innermost circle is the first day of the study. The outermost circle is the last day of the study. So the colors refer to different activities and locations. So the blue, for example, refers to when this patient is asleep in bed. And as you can see, if you look at the blue color in the inner circle, you see that it is very fragmented. So the sleep was terrible at the beginning of the study. But as the study continued, again, this is 2 months of data, you can see that the blue, I don't know whether this works, but you can see the blue there is consolidated. So his sleep has improved drastically throughout the study. You can see also that the whole graph is full of green color. So green refers to when he sits on this chair, like you see this chair here, like where the blue is. So he really liked to sit on that chair. And what you can see here is that this is a very sedentary person. He wakes up, sits on a chair. That's almost all that he does in his life. This is very worrisome, of course, because once you have an elderly person and they are very sedentary, it escalates their problems. Another thing that is really interesting is there is a yellow cone around 8 a.m. in the morning. So you see between 6 and 9, there is this yellow cone here. Yellow refers to when he goes to the bathroom to do his toileting and showering. So this is a person, you see the blue stops around 4 a.m. in the morning. He wakes up around 4 a.m., sits on a chair, and waits exactly until 8 a.m. to go to the bathroom to do his showering and toileting. Can you guys guess why? What does that mean? So I can't hear properly, most likely because of the mask. But I'm guessing some people probably have guessed it. This is someone who actually cannot shower and toilet on his own. He's waiting for someone to come to help him. And if you remember, I told you that he lives in an assisted living community. So actually, the worker comes around 8 a.m. So the person wakes up, and he's not healthy enough just to do simple things that we take for granted, like showering. And he's waiting for someone else to come and help him. And another thing that you can see, there is a cone of white before 18. 18 is 6 p.m. So between 17 and 18, between 5 and 6 p.m., he actually is outside the room. White refers to being outside the coverage area of our wireless device. So he's outside his unit. And he likes every night to go and have dinner with the rest of the assisted living community. And he tries to do this every day, as you can see, except actually there was one day you can see like here actually, he came back early. He wasn't feeling well. And again, imagine like all of this information about his health and behavior without even asking him to wear a sensor or to do anything. Just by putting something that looks like a Wi-Fi router, but just slightly smarter than that. Now, one of the other things that is really interesting is that clinically meaningful. Okay, so these are behavioral symptoms. But actually, we use the clinical gold standard, which is something called UPDRS in Parkinson. For you guys, all that you need to know is that on this x-axis is the gold standard used for assessing Parkinson. On the y-axis is the unscripted gait speed that we measure. And as you can see, they are highly correlated. There is no need to go to the clinic to do those measurements. You are getting very highly correlated from measure from the patient's home. I'm going to very quickly tell you something about our investigation of COVID-19. So in COVID, as you know, it's a respiratory disease, and we were asked to monitor people in assisted living communities because, I mean, as you remember, in retirement home, there was many cases, and it was pretty dangerous. So we monitored those patients, and our interest was to discover whether the recovery was smooth or they are having difficulty because they are quarantined. When you have COVID, the person is quarantined, and these are old people, and the nurses were very worried that the person may have escalation in their symptoms, and there is no way to detect it. So this is the breathing of a patient, and as you can see, the breathing on her breathing on April 7, and you see her breathing on April 11. And as you can see, the breathing 4 days later, like from April 7 to April 11, is much lower rate. So her breathing rate went down from 23 breaths per minute to 18 breaths per minute, which is significant. And this is nice. I mean, basically, this is what happens when you have smooth recovery. The breathing is going back to its baseline. Similarly, when you have smooth recovery, the person is moving much faster, as you can see here. So the green dot here is the patient. In both cases, you see April 8 and April 11, and you see how much faster the patient is moving on April 11. So that means they have less fatigue, they are more agile, and so on. The recovery is good. It's not always good. Sometimes we see like these breathing. This is actually the breathing of person. You remember like before, like I showed you the breathing, the nice sinusoid of the healthy person. This is actually the breathing of one of the COVID patients. Is very irregular and has like problems both in amplitude and in periodicity of the breath. Breathing actually is very important. Of course, COVID is a respiratory infection at the end of the day. So one of the things that we discovered is that if you can monitor breathing, you can tell a lot about the recovery and whether it's smooth or not. So let me explain this graph. Each one of these blue curves is a histogram of the breathing rate on one day of the patient. So the first one is on April 8. And as you can see, the breathing was improving. The breathing rate was decreasing, moving away from 20. Then on one day, the breathing rate jumped all the way. And indeed, the patient ended up in the hospital. The patient spent about 1 week in the hospital and then came back. And again, you can see the breathing rate is decreasing, and eventually the patient has recovered. So one of the things that you know when you have the ability to measure breathing like this, it was COVID, is that you hear all the time about these 3 types of patients. Patients whose recovery is not smooth and they actually end up in the hospital, like the one that I showed you. Patients who actually had severe symptoms but eventually recover and the breathing rate keeps improving until they recover. And asymptomatic patients whose breathing was always good. I mean, if you look at their vital signs, everything is fine. They are completely asymptomatic. With this, I will stop here and take questions. Actually, one thing before taking questions that I want to emphasize, of course, we have a technology that is very, it's powerful. It's getting information about health and get to see a skeleton of a person's wall. So one of the things that are very, very important to us is privacy and security. So because also particularly we work in the healthcare domain, so everything has to go according to IRB approval. There is a protocol, there is an informed consent, and also there are all of the measures about anonymization, separation of data from any PHI. In fact, we don't keep in our system any PHIs. And we pay a lot of attention to issues related to privacy and security. I'll stop here, and if there is any time for questions, there are 7 minutes for questions, so I take questions. Thank you. Yeah. Oh, there are questions here. OK. What happens if there are other disturbances in the room, such as a cat enters the bathroom? OK, and there is a smiley face after that. So I showed you that, for example, when there were 3 skeletons moving, so we can track different people and different entities. Of course, a cat will look, we didn't train with cats, so it will look, I think, like a person on the floor, or maybe like crawling on the floor. But basically, we can detect different entities, and we can separate them based on how they look and their behavior, classify them too. In fact, in our medical study, we classify the person of interest versus everyone else that we are not interested in tracking. OK, another question. Over what range can this wireless signal identify people? So basically, it's kind of like it's easy to think about it as slightly lower range than your Wi-Fi. So I'm sure all of you know that there are certain regions in your home that maybe the Wi-Fi doesn't reach. And definitely, if you have 2 floors and the 2nd floor is you need to put either a repeater or another router. So it is the same concept. So typically, we can go up to 14 feet from where the device is. If you are measuring motion, if you are measuring pulsing of the blood, then it is less. It is a few meters. But you can put repeaters to, similarly to how you put repeaters for a wireless router, for example. Other question. If there is a range limitation to the, is there a range limitation to the technology today? So I answered that. Of course, like any wireless signal, it has certain range limitation, and then you can expand it with repeaters. How does this work through? How does this work through mediums like concrete and/or metal walls, like in an industrial warehouse? So again, the type of wall is like the thicker the wall. The more dense it is, the more it's going to attenuate the wireless signal. So this is not a technological limitation. It's really more a limitation of what does the FCC allow for a particular application. So you can always increase the power of the signal if the FCC allows you to go for that power level for that application in that particular location. Seems very similar to Xander, Cardian, I don't know, something, millimeter wave radar. So, I mean, I don't know the detail of this. We don't use millimeter wave. Millimeter wave do not traverse walls that well. This particular, like I don't know this particular web page that you are mentioning, but I don't think that this actually, that they have been proven to like give any health-related information. I think radar, like people have in DARPA and military situation, try to track people through radar. And the best that they can do is a dot on the floor, like the first thing that I showed you. And even our dot is much more higher accuracy than, as far as I know from our publication at the time, it was higher accuracy than all the literature. Which frequency do you use to detect the body? So we actually use frequency that have the same carrier as Wi-Fi. So it is around the same as 6 gigahertz, 6 gigahertz. But our signal is much lower power, and it's wider band. An obvious application would be for live monitoring in assisted living facilities. Do you have any research data experience in this environment? Yeah, of course. I mean, I showed you many of these, like many of the data that I showed you comes from assisted living communities. We work with some of the assisted living communities here around the Boston area, and we have helped them during their COVID, the time of COVID and the quarantine period. OK, so I don't see more questions. So if the audience have something, then I can answer that as the last question.
I had a question, Dina. Can this
Sure.
be used as like a lie detector type application?
So this is very interesting. I don't know why you are interested in detecting lies. I can tell you as a professor, like when the student tells you that they didn't cheat on their take-home exam, you really want to know whether that is true or not. But so in principle, yes, although we did not go all the way to like test it in that environment, but basically lie detection relies on all of these like things that you do, like basically your breathing, your heartbeat changes, basically you fidgeting, all that stuff that people tend to do when they are not saying the truth. So in principle, I would say since it detects these kind of features and you can train to detect lies or like score how likely somebody is saying the truth. OK, do we have more time? There is.
One question.
OK.
In a room with 10 people, can you ID the person?
Can you ID the person? So we did our recent work on identification. And we had many more people than what you described. But I'm going to point you toward one of our recent publications about identification. Yes. And I'll take the last question, the person in the back.
Have you partnered with mobile carrier and cell phone technology for this?
So that would be a very interesting partnership, as you could guess, which is basically, I would guess like one application of this is like augmenting existing like cellular hotspots or applications so that we can have like smart environment, smart home, smart analytics. And currently we haven't partnered with any of these providers, but that would be an interesting thing to consider for the future. Thank you very much.